Good afternoon.
Good afternoon.
So, how's everyone doing? Any problems with the quizzes or anything yesterday? All right, I guess not. All right, well, let's go ahead and let's see. Who are we missing at Moyan? Hannah? Sent, right?
Yeah.
All right, and let's see. It looks like everyone's there at St. John's. So let's see, Nathan. Did you figure out a schedule for when you wanted to make up some of those quizzes in that test?
Yeah, if I could do, I want to say, how fast do I have to make these up?
I'm not going to put pressure on you here. I mean, I want you to be prepared for them. So if you need a little time, that's okay.
Starting next week, I could do one every day, or not every day, every Mondays, no, let's just say Tuesdays, Wednesdays, and Thursdays at 3:40 p.m.
Okay, so if you'll talk to Crystal.
Yeah.
And work out the schedule and then send me an email and I'll make sure I have it open those days, okay?
Okay, cool.
And then if it turns out that something else happens and you can't do it one day, just let me know, okay?
All right.
We'll figure it out.
Cool.
Or if you need a little extra time, whatever, that's okay. All right, let's see. Okay, we're all there in Winslow. All right, so so today, what our plan is we're in the middle of 2.5 on continuity, and so we will continue with that. Any other questions, comments, concerns before we get started here today? Okay. Well, let's go ahead and do it.
Is that a Darth Vader tie?
That is a Darth Vader tie.
I approve, yes.
You approve? And I think that's Luke down here at the bottom, battling Darth Vader. I don't know if you can see it, but anyway.
I can't. And between Luke and Darth Vader is better.
I'll stand up and see if that helps. But do remember that Luke kind of defeats Darth Vader, or at least I don't know. You got to give it to Luke because he defeats the Emperor and Vader. So anyway, I saw this thing that said that Luke might have been the greatest Jedi that ever lived, and that's why. Is that anyway? He destroys the Death Star, Vader, the Emperor. I mean, who does that?
I would argue, though, that Darth Vader wasn't willing to fight Luke because he knew Luke was his child, so he wasn't going all out on Luke. Yeah, and the Emperor, according to the recent Star Wars trailers, Emperor Palpatine isn't dead yet, and technically Darth Vader defeated the Emperor because he's the one who actually tossed him off the edge.
That's true, but I would say that I'm actually irritated with trailers in general because I think that they reveal too much of the movie, especially if it turns out that the Emperor is not dead. It could be his clone or something, but anyway, I hate that's in the trailer. I hate it. Episode 1 was ruined for me when the trailer revealed Darth Maul and the double-bladed lightsaber. If you hadn't seen that before the movie, anyway. It's funny because I was just talking to somebody today about how I'm so anti-trailer because they spoil too much. And that was the brilliance of, I thought, Avengers Endgame, is they revealed nothing in the trailers. So, anyway. All right, well, let's go. I kind of agree, though. All right, so we're on part 4, so 2.5. part 4 on the front side about the greatest integer function. So this is just because greatest integer is not something that we use all the time. Just wanted to remind you that it's on the calculator, the math menu. Let's see, let me pull that up. Okay, there we go. So if you go to the math and then arrow over to number and then option 5, int, that's for the greatest integer function. And so we were talking about continuity. So this is what the greatest integer function looks like. It's the step function. So if you wanted to know where is this function continuous, well, it's continuous everywhere except at the integer values, because at the integer values, it jumps up to the next step. And so we would say the function is continuous for reals that are not integers. Or the way you could write that in math symbols is the set of real numbers that are not integers. Okay. So let's see if you can either kind of by reasoning or putting it in your calculator, see if you can figure out where is the greatest integer of x plus 1 continuous. All right, Chloe, what do you think?
One second, I'm just putting it in.
Okay, no problem.
I'm not sure. It said that I was wrong. It said it was undefined.
Oh, it wouldn't graph it?
Yeah.
Okay, so let's make sure that you're putting it in right. So if you go to the y equals, so and then you do the greatest integer, so math number 5, so int, and then you type in x plus 1, x plus 1. And then close that off. And then I'm going to just graph that on the standard viewing window. So zoom 6. And so this is also a step function. Did you get it to graph this
Yeah,
time?
yeah, I have it. I have it here now.
Okay, so where are those jumps? Where are the breaks, the discontinuities?
Every one.
So yeah,
Every
so,
like 1 unit.
And again, it's at the integer values, right? So 1, 2, 3, 4. Okay, so every integer value. So it's similar to the last one. You would say, see, if you want to know where is it continuous, well, from 0 to 1, 1 to 2, 2 to 3, or you could, again, it's all real numbers except at those integer values, because that's where it jumps up. All right, any questions on that? Okay? All right, so there's 4 types of discontinuities. Jump, removable, or that's a hole in the graph. We call that a removable discontinuity. Infinite and oscillating. So I don't know if you need a picture by each one, but I'm going to show you a picture of each one. Okay, so this first one is, this first graph is continuous. Okay, but then when you have a hole in the graph, whether it's defined, the point is defined somewhere else or not, whenever you have a hole in the graph, that's a removable discontinuity. When there's a break in the graph like this, that's a jump discontinuity. When you have a vertical asymptote, that's an infinite discontinuity. And then oscillating is where it goes up and down and it doesn't come together. Okay? So if it doesn't come together and you have to pick up your pencil because you don't know if these match or meet up or not, you have to pick up the pencil, it's going to be a discontinuity. So this is oscillating, where it goes up and down so much you can't tell if it meets or not. Okay. All right, so a function is continuous on an interval if the function is continuous on every point in the interval. So if there's a discontinuity in the interval, then it's not continuous everywhere. That's sort of an obvious statement, but it's worth saying anyway. So here, this function is continuous everywhere except at x equals 0, because there's a break in the graph. And what kind of discontinuity is this?
Infinite.
Infinite. So if I ask where is this continuous, then you could answer either of these ways. You could say from negative infinity to 0, and then from 0 to infinity, or you could say all real numbers except 0. Okay. Wait. Okay, now this is the properties of infinite, of continuous functions, excuse me. But I decided to not really have you write these down because everything works the way you think it should work as far as continuous functions. If you add continuous functions, the sum will still be continuous. Or if you subtract, or you multiply by a constant, or 2 functions that are continuous, you multiply them together. Division, square root. Really, the only thing you have to worry about is the same thing you worry about with regular functions. You have to worry about zeros in the denominator and negatives underneath radicals. You still have to worry about those. Okay? So, is y equals 1 over x squared, is that a continuous function? So what do you think?
No.
No. Where is it not continuous?
0.
At x equals 0. Because that gives you a 0 in the denominator. So it is continuous everywhere else, but not at x equals 0. Okay, very good. Okay, next, algebraic combinations of continuous functions are still continuous. So that's kind of like what we were saying is if you add two functions and you combine like terms or whatever, that combining algebraically doesn't mess up continuity. The only thing that messes up continuity, zeros in the denominator, negatives underneath the radical. Okay? Those are the things that you have to look out for. Okay? So, for example, if I start off with a continuous function, f of x equals x squared, and here's another continuous function, g of x equals 2x minus 1. If I combine those, if I say the g of f of x or the f of g of x, that's not going to mess up the continuity. Okay, so even when you do composite functions, okay, and we'll talk more about that. But just manipulating, that doesn't throw off the continuity. Okay? All right? So go ahead and write down your answer to this one. All right, so Aiden, what do you think?
Turn it on. Oh, it's not continuous at 3 and negative 3.
That's exactly right. Because now just dividing, 2 is continuous, x squared minus 9 is continuous. Dividing those doesn't mess it up, but you got to look out for zeros in the denominator. So it's kind of like if I said, where is this function defined? Everywhere but 3 and negative 3. Where is it continuous? Well, it can't be continuous where it's not defined. So you would still have to throw out 3 and negative 3. So, or anytime you have vertical asymptotes, that's what that means. The discontinuities occur where the vertical asymptotes occur. All right. All right, continuity of the absolute value function. The absolute value function can be broken down into what two polynomial functions? Well, it can be broken down into y equals x and y equals negative x. So you put those two together. So it's y equals f of x equals x if x is positive or 0. F of x equals the opposite of x if x is less than 0. So you have these two lines that come together. And so because they come together, then the absolute value function is also going to be continuous. Now, sometimes we're going to look at functions that we're not going to know for sure if the parts come together or not. And that's going to be the big question is, do they come together and meet, or is there like a gap or a jump or something else going on? That's going to be what we're going to have to look at. But the absolute value function, and you probably could know that from college algebra, you know the absolute value looks like this, and that would be continuous, okay? All right, so which of the 6 trig functions are continuous? Okay, so think of the 6 trig functions and write down the ones that you think are continuous. All right, Nathan, what do you think?
Sine and cosine.
Sine and cosine. That's it. Because all the other ones, all the other ones have vertical asymptotes. And so they all have infinite discontinuities. Okay? So it's just sine and cosine because they go on forever in both directions. Any questions on that? Okay, so going back to composite functions, if f and g are continuous functions at a point, then the composite is also continuous. All right, so see the square root function is a continuous function. Okay? This polynomials are continuous functions. So by putting the polynomial under the square root, that's not going to mess up the continuity. So the function is continuous. Now, if I need to know where, if the problem says where is it continuous, then you would have to say, where is this greater than or equal to 0? So the radicand. You would set that greater than or equal to 0 and then solve. Okay? All right, so let's see if, so for practice 8, where in the respective domains is this continuous? Okay, so see if you can figure that out. Got to do a little algebra with that one. All right, so Rachel, when you've got it.
Is it plus or minus the square root of 1/6?
All right. So let's see. No. So let's go through it here. So it doesn't factor. So you want to use the quadratic formula. And so when you work through, you get 6 plus or minus radical 32 over 2. Now, at that point, I would look to see if, if this is a quiz question or a test question, I would look to see if your answers are in radical form or if they're in decimal form. Because if they're in radical form, then you want to continue simplifying. If they're in decimal form, then I would just bail at this point and put it in the calculator and get the decimals. So 3 plus or minus 2 radical 2 is what we would be looking for. Okay, does that help, Rachel, or do you need me to go through it in more detail?
Actually, could you go through it in a little more detail?
Sure. Okay, so if here we take, so what we're looking for is that a radical can only be continuous where it's positive. You don't want to have a negative underneath the radical because then you'd have a complex number. So we're looking at what would make this greater than or equal to 0. All right, so then what we do is we'll say, A is 1, B is -6, C is 1. So x equals the opposite of b, plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. So that's 6 plus or minus the square root of 36 minus 4 over 2. So 6 plus or minus the square root of 32 over 2. And square root of 32, that's 16 times 2. Square root of 16 is 4. So 4 radical 2 over 2. So what I like to do when I have radicals is I split them up. So it would be 6 over 2 plus or minus 4 over 2 radical 2, which would be 3 plus or minus 2 radical 2. Okay, so those are the x values. So that's like where it crosses here and here. And so then what you're looking at is then to say, okay, so it's, where is this graph above the x-axis? Well, from negative infinity to that first point, 3 minus 2 radical 2. And then the second point is from 3 plus 2 radical 2 to infinity. Okay. All right. So is that okay, Rachel, or are you still confused or what?
Could you just scroll down a little bit so I could get the rest?
Sure. Now, if you have trouble here with the radical or whatever, you could actually just solve it with the calculator and just graph the original radicand, and then you want to know where is it greater than or equal to 0. And so you could use second calc 0 to find those decimal values. You could do it that way as well. Say, where is the graph of greater than or equal to 0? Where is it above the x-axis? Okay. All right. Let's go on here. All right. So where is this? Let's say, where is this not continuous? And then we'll figure out where is it continuous. Well, however you want to say it. All right, Skylar, what do you think about this one? Where is this not continuous?
I have no idea.
Okay. Well, let's start with, what are the two things that you have to look out for? All right, can anyone tell me?
A 0 in the denominator.
Zeros in the denominators, and then I said negatives underneath the square root. But see, this is actually a cube root here. See, you can have negatives underneath the cube root. That's not a problem. So there's no issue at all with the numerator. Okay? The denominator, is there anywhere where that any value for x that can make that go to 0?
No.
No. So then what does that mean? Go ahead, Joey.
I don't know.
Or anybody. If there's no zeros in the denominator and we don't have to worry about radicands, then what does that mean?
It's continuous.
It's continuous everywhere. Okay? And we didn't have any problem with this one. So, and you can graph it. Now, to determine continuity with the calculator is a little risky because, I told you about the the holes, the removable discontinuities, they don't show up on the calculator. So, but this is what the graph looks like, and it is continuous everywhere. But so for all real numbers, this is continuous. Have no holes, no asymptotes, no zeros in the denominator, no negatives underneath square roots. Okay?
So why did the last one have to have the greater than or equal to 0?
Because it's a square root. And square roots are not defined for negatives. That's how we get the i's, the complex numbers. But cube root, you can have the cube root of a negative. So any odd index of a radical is okay. You can have any real number under there. But if it's an even index, like square root, fourth root, sixth root, square root's the most common, but you can't have any negatives under there. So you have to say it has to be greater than or equal to 0.
Okay.
Okay? Thank you for asking that. Let me clear that up. All right? So, see if you can tell me where this is continuous. All right, so Dalen, when you got it?
2. Like it's
Okay, so 2, it's discontinuous. Why?
Because when you plug in 2 to that equation, it equals 0, and you can't have zeros in the denominator.
No, wait. Okay, you said it equals 0. What's the it that you're referring to?
That equation in the denominator, you plug into...
In the denominator. See, if you say the equation or the function is equal to 0, that's okay. But it's when the denominator is 0, that's not okay. You understand the difference? What I'm saying here? So you can have this equal, like you can plug in 3 or negative 3 and have a 0 out of this, and that's fine. But you're right at 2, because that makes the denominator go to 0.
Oh.
Then it's not, so it's continuous everywhere except at 2. Now, so I used to, instead of teaching this for college credit, I used to teach it as an AP class. And so that was always super stressful. Could you imagine having to take a test at the end of the year to determine if you got college credit or not? I mean, that you talk about stress. But anyway, one of the things that I was always, I found out that the graders look at, and so I became very aware of, is whenever a student says it, that usually they would count it wrong. So if they would say it equals 0, then they would say, well, that's not enough. And so they'd circle the word it and no points. So anyway, so I found myself just being a real stickler for, you making sure you don't use it as much, if you can help it. Anyway, it drives my wife crazy now, but I've been scarred for life on that. So the denominator is 0 at 2. Okay, so try this one. All right, Jordan, when you've got it.
All reals except for 0.
All reals except for 0. It's continuous for all reals except for 0. Now, what if I canceled the x's? Is that legal?
No, because the x's are tied to the equation above.
Yeah, so it's legal in the sense that it's going to be the same graph. But if you remember when we did limits, what happens is when you cancel the x, basically what you're doing is you're plugging in the hole. So in the original equation, this is discontinuous, right how Joran said, all real numbers except 0. The second equation, after I cancel the x's, now this is continuous everywhere. So by canceling the x, what I'm doing is it's like plugging up the hole. And so we'll talk more about how to do that, how to make a discontinuous function continuous. Okay? All right, any questions on that? By the way, again, I just want to emphasize, if I take my original function and put it in the calculator to graph it, it will not show the hole. And so if you just graph it and say, oh, this is a continuous function everywhere, wrong, because it's not showing the hole at x equals 0, which would be right here. It doesn't show that. Okay? So, good job. See, Jordan, you're smarter than your calculator. Okay? All right, next. Limits of continuous functions. All right, so if you have a continuous function, basically when you are applying limits and when you're calculating limits of a composite function, you can just calculate the limit and then plug it into the other function. There's nothing really tricky or sneaky about this, except that sometimes it looks like a real scary limit. But the fact that you have a composite function, it doesn't change the value of the limit. You can still do it, okay? So let me give you an example here. So see this right here, the cosine
Excuse me,
of...
Mr. Strong.
You need me to go back?
Could you just go back for 1 second? Yeah.
Yeah, sure.
Thank you.
Sure.
Okay, thank you.
You bet. So the fact that this is more complicated than any limit we've ever done, okay? It's okay, because even though, if you just start in on the inside and work it out, and it will still work out, even though it's a composite function. So the first way that we have to do limits is to plug in. So what I'm going to do is just plug in pi halves for x, okay? So then I'll get 3 pi halves plus pi halves is 2 pi. Well, then the sine of 2 pi, that's all the way around the unit circle, the sine is 0, okay? So I just have gotten to there. Well, 2x plus 0 is 2x, but see, now I can plug in again. Well, the cosine of pi is going to be -1. So that's the answer, -1. So it's just plugging in and working it out. Okay? All right, so go ahead and see if you can do that complicated looking one there for practice 9. All right, so Hannah, when you've got it.
I'm kind of lost right now. If you could.
Okay. All right, so did you try plugging in -2?
Yeah, but I don't know. I just can't I don't know what I'm doing wrong.
Okay.
But
Well, when you plug in -2, what do you get?
you would get 0 in the denominator.
Right. And actually you'd get 0 in the numerator here too. -2 squared is 4 minus 4, so you get 0 over 0. Okay? So what I'm testing here is if you remember what to do with limits when you get 0 over 0. So this is back in chapter 2. What do you do when you get 0 over 0? Anybody?
You factor the top, and then
You factor and see if you can cancel. So this numerator here factors to x plus 2, x minus 2. Here, let's write that up. Now, let's see where. Okay. So we'll write that. So the limit as x approaches -2 of the sine of x plus 2, x minus 2 over x plus 2 times pi fourths. Okay? So now you can cancel the x minus 2's and then plug in again. Okay? So try that, Hannah. So Hannah, when you plug in -2 now, when you cancel the x plus 2's, then what do you get?
Zero?
You get 0. So because what you end up with, when you plug in -2, then you end up with -4. So you have the sine of -4 over, let's see, so you plug in -2 here, and you get the sine of -4 times pi fourths. Okay? So the 4's cancel, so you end up with the sine of -pi, which is 0. Okay? All right. Any questions on that? Okay. All right. So the last really big idea here, well, no, I guess it's the second to the last, is what's called the intermediate value theorem. Okay? So the intermediate value theorem says that if we have if f is a continuous function, so like let's say that this function goes from this point 2, 2 to 5, 7. then if this is a continuous function, then the function takes on every y value between 2 and 7. So if you say, well, what about like 3.1? What about 6.7? What about 2.395? Then the answer is yes. Somewhere, every y value between 2 and 7 has to be on there somewhere. Because it's a continuous function, so there's no gaps or holes. Okay? Now, this is not a continuous function, so not every y value is reached. But if we have a continuous function, then every function, every y value is reached. So this says, show that there is a zero of the equation y equals x cubed minus x minus 1 between x equals 0, between 1 and 2. Okay, now I know this sounds like a weird question to ask, okay? But this is actually how your calculator finds zeros for you, okay, using the intermediate value theorem. So let me just show you. It's a pretty cool idea. Is you just say, okay, let's plug in 1 into the function. Well, first of all, you do need to say that it's continuous, okay? So then you plug in 1 into the function, and you get a negative 1. Then you plug in the second number, and you get a positive. So if one y value is negative, and one y value is positive, then that means it has to cross the x-axis. It's somewhere in between, the y value has to be 0. Okay? And so then there must be a 0 between x equals 1 and x equals 2 because of the intermediate value theorem. So the function's continuous, and one y value was positive. It doesn't matter what it is. As long as one's positive and one's negative, it has to go to 0 somewhere in between. Okay? All right, so go ahead and try practice 10. I don't know if we'll have time to finish going over it, but go ahead and try it. Practice 10. All right, I think we're going to run out of time before we go over that. So finish that one, kind of write it up, and we'll start there on Monday. Okay? And then Aiden, I'll look for, or Nathan, I'll look for an email from you for next week. And I hope you guys have a great weekend, and we'll see you next time. We'll see you.